All right, let's talk about one of AI's biggest hurdles. I mean the real world, right? It's messy, it's unpredictable, it's just plain confusing sometimes. Today, we're diving into a really cool, groundbreaking new way to help AI handle all that chaos, all that unknown.
So let me just ask you this straight up. What do you think is AI's biggest blind spot? I mean, we see it doing all this incredible stuff, right? But underneath it all, there's this one fundamental kind of uncertainty that it's always struggled with. And it's something that, basically defines what it's like to be human.
And here it is. It's the huge difference between risk and ambiguity. Now, AI is a rock star when it comes to risk. You can teach it the odds of a coin flip, no problem, because the rules are clear. But ambiguity? Whoa, that's a whole different beast. That's when you don't even know what the rules of the game are. It's the messy, unpredictable nature of real life, and trust me, that is a way harder problem for an AI to get its head around.
So, how in the world do we get an AI to deal with that? A world where the rules can change on a dime, or, you just don't know them at all? Well, that's where this really powerful new tool comes into play. It's called Neural Expectation Operators, or NEOs for short. And you can really think of them as this incredible new bridge, connecting some super deep mathematical theory with the practical, hands-on world of AI.
Okay, so what are these NEOs really? Well, from a bird's eye view, they're a framework that uses neural networks to model something called nonlinear expectations. And don't worry about the jargon. The idea actually comes from economics. It's all about trying to model how we, as people, make decisions when we're faced with genuine, deep uncertainty, not just a simple, calculable risk.
And that whole constructive bridge idea, that is absolutely key here. See, NEOs aren't just some abstract theory stuck in a lab somewhere. No, they are built from the ground up to connect this super deep math. We're talking about something called backward stochastic differential equations, which is just a fancy way of saying equations that work backward in time to figure out uncertainty with the actual tools that machine learning experts use every single day.
Okay, that all sounds really cool in theory, but how does it actually work? Like, what's going on under the hood? Well, the engine driving this whole thing is a new concept the researchers are calling measure learning. And this measure learning idea is the bedrock of everything NEOs do. It's a totally new way to think about modeling ambiguity. Instead of trying to pin down one exact probability for something, it's about learning to understand and represent the entire landscape of what's possible, all the uncertainty all at once.
We can actually boil this whole complex idea down to 3 pretty simple steps. First, you start with that powerful math framework we just talked about, the BSDEs. Then, you plug in a neural network to act as the driver, the engine, for that equation. And third, that combination, that's the magic. It lets the system model all that messy ambiguity using those nonlinear expectations. It's this beautiful, elegant mix of pure mathematics and real-world AI. But this next part is where it gets really cool. I mean, truly genius. Because the big innovation here isn't just what NEOs do, it's how they're designed. It's about literally building mathematical guarantees right into the AI's DNA, into its very architecture.
See, the old way of doing things, the old mathematical rulebook, it had a huge flaw, a deal breaker, really. It depended on something called a global Lipschitz assumption. Now, you totally don't need to be a mathematician to get this. The key thing to know is that this assumption was like a giant stop sign. It meant all this powerful theory was completely incompatible with the kinds of neural networks that everyone actually uses today. The best, most effective ones couldn't use them.
And that is what makes this such a huge breakthrough. By creating a new theorem that just sidesteps that old broken assumption, NEOs basically unlock an entirely new toolbox for developers. All of a sudden, they can use the normal neural network designs they're used to. They can use standard tools like ReLU activations. They can finally take this powerful theory and apply it to a way bigger range of problems. It finally makes all this incredible math actually usable.
So here's the real paradigm shift, the big idea you need to walk away with. Instead of using math to check if a system works after you've built it, NEOs use the mathematical rules as the actual blueprint to build it in the first place. Things like convexity aren't just hoped for, they are baked right into the neural network's design. And what that means is the AI is guaranteed, literally guaranteed, to behave reliably right from the get-go. It's like building a skyscraper where the laws of physics aren't just a guideline, they're embedded in every single steel beam.
Okay, so we've got this incredible new tool. It's mathematically solid, it's built right. So what? What's the big payoff here? What can we actually do with this that we couldn't do before? Well, this is where we get to see the true power of NEOs, unlocking our ability to understand some insanely complex systems.
we're talking about applications in areas that were just off limits before. They were too complex to model in any reliable way. For instance, NEOs can help us analyze systems where the future actually affects the present. Think about things like finance or economics. It's a huge deal there. And they can also help us understand how huge groups of individual things behave together. Whether we're talking about molecules in a chemical reaction or thousands of traders in a stock market.
And because we can now model these systems with so much rigor, with so much mathematical certainty, it lets researchers do something that was pretty much impossible before. They can now prove that some of the most fundamental, bedrock principles of math and statistics still work. They still hold true, even inside these wild, complex, and ambiguous worlds.
And what's one of those huge principles? The law of large numbers. Yeah, being able to prove that. It's also called propagation of chaos inside these complex systems. That is a monumental achievement. It basically proves that even in these crazy, chaotic models, the behavior of the whole system can still emerge predictably from the sum of its parts. This isn't just a small step forward, it's a giant leap for both mathematics and for what AI can do.
All right, let's wrap this all up. If there's one thing you take away from all this, it should be this. Neural expectation operators, NEOs. They give us a mathematically solid, structurally guaranteed way to make AI not just smarter, but way more reliable, especially when it has to face the messy ambiguity of the real world.
And that leaves us with one last big question to think about. If we can now build AI that isn't just powerful, but has reliability, mathematical guarantees built right into its core, what kinds of massive problems can we finally truly trust it to help us solve? Think about science, finance, medicine. The possibilities are just starting to open up.